Awesome. Thank you, Drace. I'm going to start sharing my screen now, and please let me know when you are able to see my screen.
You're good to go. We're able to see it.
So hey everyone, my name is Philippe Heitzmann. As Drace mentioned, I am a student at the NYC Data Science Academy Bootcamp program. And today I'll be presenting the fourth and final capstone project that I completed as part of the bootcamp curriculum on predicting loan defaults on the LendingClub platform with machine learning. What I'll be talking about today is sort of some of my journey leading up to the bootcamp, my background in data science and machine learning, how I got interested in joining the program, and some of the things that I learned during the program, and how I applied a lot of the things I learned in, for example, Python and R in this bootcamp, in this capstone project, here to also answer any questions that you guys might have on, things that you learned in the bootcamp, or anything that you guys might be curious about. I'll start as well by dropping in the chat the link to the web app that I created to present this project as well, which I encourage everyone to look at as well during while I'll be presenting. The web app includes some interactive graphs that I created to let users play around with some of the data and get a better idea of the data itself. So I encourage everyone to sort of play around with that as we go along. If I can just find the chat button.
It's going to be either hovered towards the top or the bottom. It's a little bit on the annoying side. Yeah.
Yeah, if everybody, I included it in chat at 6:03. So if everybody wants to scroll up in the chat as well, the link is there. I'm just having a little bit of issues finding this, but it is in the chat if everybody wants to check that out. Before I start the presentation, I just want to also provide the disclaimer that any opinions and positions that I will be presenting in this presentation are not representative of those of any entities with which I've been affiliated, past or present or future. So just want to also get that out of the way. Now that's out of the way, a little bit of background on myself. I graduated from Duke University about a year and a half ago with majors in economics and international relations. I had very little background coming out of university in programming or data science or machine learning. And I started working full-time in the financial services industry, more specifically in sales and trading, right out of college, and sort of dealing with data on a day-to-day basis, mostly in Excel VBA. I kind of got a feel for some of the things that were possible with dealing and analyzing data, and quickly got really, really interested in trying to better understand some of the more technical tools that are available out there, mainly Python and R, and trying to get a better handle for those. Naturally, that led me to the bootcamp program, which I started in April of 2020. I started as I was working full-time and still am working full-time, started on the part-time online track, which lasts about 6 months. And during that, completed the normal bootcamp curriculum that full-time students will complete in 3 months, and completed 4 different projects. And today I'll be presenting the 4th project that I completed, which is this capstone project on predicting loan defaults on the LendingClub platform. So this is sort of the project outline for this project. I'll be walking you guys through number 1, sort of the main question: why should we even care about wanting to predict loan defaults? Number 2, going into some of the background of the LendingClub platform, which is where we source our data from, and basically it just based all of our machine learning off of. Number 3, walking you guys through the research goals, what we're trying to predict, and what are some of the visualizations and ways we would want to be displaying the data as well behind that, and sort of taking a full stack approach, not only doing a lot of machine learning and data science, but also trying to actually create useful tools for users to leverage in order to use those predictions in whatever settings they might be interested in. And then the sort of 4 to 8 are sort of the usual data science processes that if you guys join the bootcamp, or if you guys have any experience in data science, will know about. Walking through exploratory data analysis and some of the more standard data pre-processing, feature engineering, and selection, which are always sort of maybe less fun, but always very necessary parts of the data science process. And then going through the actual machine learning and sort of meat of the project, and then walking through the results and the conclusion. So the first question, which is a fair one always, is why should we even care about predicting loan defaults? Really, trying to apply machine learning to predicting loan defaults is something that's extremely useful for private companies looking to minimize their capital losses on credit that they're extending to some of the users on their platforms. Credit card companies or banks or credit unions are big examples of this. And of course, behind that is always trying to maximize your bottom line and trying to predict whether a user or a client is going to default on their loan in order to try to maximize your bottom line. For financial regulators, this is also extremely important when trying to better forecast capital ratios and loss reserves to make sure that the financial system is sound, that banks and credit card companies have enough capital behind some of the loans and the credit that they're extending, so that in the case of some sort of major macro downturn, they're still in a good financial position to deal with those unexpected losses. And so that there isn't a systemic risk to the financial system. And then finally, also for financial regulators, this is always extremely important those models, those machine learning models are extremely important to understand and be able to interpret because you always want to make sure that there are safeguards against financial discrimination, based on race, gender, ethnicity, and so on and so forth. So you want to always have models, machine learning models that are interpretable by financial regulators in order to ensure that all of those legal protections are in place and are being enforced and respected. So a little bit of background on the LendingClub platform. LendingClub is a peer-to-peer financing platform that launched in 2006. And essentially anybody, you and I, can sign up on the LendingClub platform if we're looking for a loan. And anybody can also sign up on the platform if they just want to invest in loans, browse loans that are available that are posted by other users to see what might be interesting to invest in. And so here on the right is a sample view of the platform where you can see different loans that are posted by users, where they'll post about sort of the title and purpose of the loan, the loan amount, what sort of FICO score the applicant has, and the term of the loan, among other information that's available to all the investors that are on this platform and looking to invest in loans. Some of the other important data that is available to investors is general information about credit history, FICO score, of course, employment status of the loan applicant, the length of the employment, loan purpose, and loan grade, which is a grade that's assigned by the LendingClub platform based on a lot of those, a lot of that data. So taking this data, the LendingClub platform provides publicly a data set comprised of 2.3 million observations of loan applications that were made between the years 2007 and 2018. So this is a lot of data to deal with. There are 151 features that encompass numerical, qualitative, or date-time variables that are available to investors for each of those observations. And so this sort of large data set is sort of perfect to apply machine learning techniques to try to create statistically significant, robust, and accurate machine learning models that you can then use and leverage to make loan predictions and try to invest in these loans. Some of the key considerations of the data set as this is a sort of classification machine learning problem, in this case, because there are, of course, more people that repay their loans than those that don't, there's a sort of a class imbalance where there's more examples in the data set of loans that are not defaulted than those that have defaulted, which is important when training your machine learning models in order to make sure that your machine learning model is prioritizing classifying correctly the loans that are going to default, as well as the ones that are not going to default. So that's sort of key consideration number one. Number two is trying to make sure to adjust for variable multicollinearity. Variable multicollinearity just means that certain variables are going to be certain independent variables, meaning the variables in here that are going to be used to predict your dependent variable, which is whether a loan defaults or doesn't default, are highly correlated between one another. And that can introduce some issues in machine learning with linear models where that multicollinearity needs to be addressed and certain variables need to be dropped, namely the ones that are really multicollinear, in order to make sure that those issues don't pop up later down the road. And of course, as with any sort of data science problem, outliers are always something to be mindful of. So, for example, looking for loan applicants in here that have, annual incomes that are above the $1 million range, when the average in this data set is about $85,000. Trying to address those outliers and on a case-by-case basis, try to see whether or not it makes sense to keep those outliers in the data set or try to take them out. So the research goals of this project were threefold. Number one was to create machine learning models that were trained on the 2007 to 2017 data that could then accurately predict loan defaults in the 2018 loan pool. This is sort of a realistic business problem where in the real world, if you were an investor, you would be always looking at the 2007 to 2017 historical data in order to train those models and make predictions on a future loan investment set, in this case, the 2018 data. Next, we wanted to create a way for investors to optimize for the best investment opportunity set, which we defined in this problem as just internal rates of return, just IRR. For the finance crowd, I think will be familiar with this term, but this just means the annual rate of return that you can expect on your investment. And then trying to make it easy for investors to leverage those predictions and those predicted IRRs to then construct a loan portfolio based on those machine learning predictions, using a web framework called Flask, and and then also deploying those models on AWS. To then have some sort of tool that allows investors to leverage those predictions. So going into sort of the standard data science process, the first stop always with any data science project that you'll undertake is just doing exploratory data analysis. I encourage everyone to hop on the link that I shared in the chat to check this out. But I'll pull it up here. In the Dash app that I created for this project, I included interactive graphs that allow the user to interactively select portions of the data and get an idea of what data is available in the data set, and and build some intuition about some of the different relationships between the independent and dependent variables, which might be useful later on when you're making decisions about which features to include or exclude, or which features to create based on some of the data that's available to you already. So in the left topmost graph up here, you'll see there seems to be a little bit of an issue with the server. I think we might have too many people on the server. But this top leftmost graph allows the user to hover their mouse over the map over a specific state, and that hover mouse, that data of the user hovering their mouse over each state will be passed on to each of the graphs in the adjoining graphs in this view to then load the data for each of those states. So you'll see so the intuition that you're trying to build is sort of high level in this case, where you're looking at a map of the United States here, where you're displaying the default rates for each state. At first glance, this is an interesting sort of view where you can see that there seems to be some sort of regional clustering in the map here, where southeastern states, Alabama, Mississippi, Louisiana display higher average default rates than other regional clusters. For example, the Northwestern United States, with states like Idaho, Oregon, or Washington displaying lower than average default rates. This is interesting because there might be some sort of macro variables at play that are dictating, why those states or those regional clusters have higher or lower default rates than average, which may or may not be captured in the data. One additional hypothesis when I was first looking at this was, well, maybe different states have different loan quality distributions, where, for example, maybe the southeastern states have a higher share of the lower loan grades, the E and F loan grades, which might explain why those, just being rated lower might have higher default rates than the Northwestern states. As you'll see in the graph on the directly to the right of this, that isn't the case. If you hover your mouse over each state in the map, you'll see that each state has the same sort of loan quality distribution, with a leftmost skew towards the A and the B grades. And so that sort of initial thought is disproven already, and we're already in a spot where we can confidently sort of say that there has to be other factors at play that are making this relationship come true in the data. Next, if you
real quick, sorry, to interject.
Yeah.
I know we can't reload the page. I'm afraid that if you reload, you're not even going to connect at all. Is there a way we can minimize the errors, the server callback errors at the moment? I think that unfortunately, way too many people were hitting the server at the same time.
Right.
I think you can on the right, like if you toggle each of them off individually. But let me.
I'm not sure.
I
think it's an issue with the AWS instance,
right,
that's not taking the load.
Yeah, and I know that if you reload right now, I think it's just going to not load at all.
Got it. Okay.
So,
I'll just walk through some of the other graphs and then go from there. It won't matter too much if it's not interactive.
Apparently, one suggestion is you can do it on the right side down near the blue button. You can. So apparently that could flip ignore the. There we go. Yep.
Got it. Okay. Perfect.
Perfect.
So
thank you, Yellow.
Awesome. Yeah. Thank you, guys. So next, looking at the left bottommost graph here, if the actual Amazon instance was working correctly, you would see that hovering your mouse over a state would feed the data here. But I invite everyone after the talk, once I'll have moved this to a stronger AWS instance, to take time to play around with this, and you'll see that these will be reloaded and will work correctly. But the top bottom, the left bottommost graph here is also very interesting because it shows the relationship between repayment rate for different loan applicants versus their FICO score, and different interest rates charged by applicant FICO score. And the interesting thing that's being displayed in this graph is that you'll see applicants between 650 and 700 FICO scores have a repayment rate between 0.9 and 1, which is pretty identical to other FICO score applicants, mainly the ones applicants that have FICO scores between 800 and 850. And the interesting thing here is those 650 to 700 FICO score applicants though they have sort of the same repayment rate as those quote unquote higher quality FICO score applicants, they're still being charged 2 to 3% more in interest rates. So this is a really interesting observation for any investor who is looking at this and thinking about what sort of loans to invest in and how to maximize the returns. Maybe there might be some sort of advantage to actually lending more money to people in the 650 to 700 range versus the sort of quote unquote higher quality FICO score applicants. And the last graph that I'll show here is this right bottommost graph where this is showing sort of the default rate by employment length for loan applicants. So going to this project, one of my initial hypotheses, as I think most people would assume, is that people with more work experience would tend to have lower default rates, would tend to repay their loans more on average than those that have lower amounts of work experience. And what actually transpires in the data is that this is not at all the case. People actually with more work experience display higher rates of default. In this case here, the blue bars are the people are higher default rates groups versus the green bars, which are lower default rates. And if this were working correctly, I would be able to sort of hover my mouse over all the different states, and this would show that for pretty much all states, this relationship holds mostly true, where on average in the whole data set, those with more work experience actually have higher default rates. So this is all meant to sort of build some intuition about what's going on in the data and build some intuition about what might be interesting to do later on in terms of feature engineering, creating new features based on all these different relationships that we're seeing already, to then extract even more information out of our data and create even more accurate and robust machine learning models. So next, going to the next step in the data science process, which is data preprocessing, which is a little less, I'd say, sexy and interesting, but always very, very important to do in any sort of data science project. Mainly, this is comprised of three main processes of dropping variables, imputing missing data, and normalizing your features. So dropping variables, mainly this has to do with any variables that have too much missing data. So in this project, I defined too much missing data as more than 50% missing data. There are different rules regarding, what threshold you want to take. 50% is sort of on the more conservative side of actually wanting to keep more data. Some people will do 30, 40%. But so in this case, using that threshold, 50%, 42 variables were dropped from this. And then, also trying to drop variables that introduce data leakage. This data leakage just means any variables that contain information that is too revealing about what we're actually trying to predict, which is loan defaults. So, for example, in the LendingClub data set, there were variables that include information on whether or not collection fees were recovered on loans, which, of course, you're only going to have a collection fee recovered if there's a default that occurs and there's a collection fee to collect. So those types of variables were dropped, and other variables that have only single values that contain essentially no information were also dropped. Next, you want to always, once you've dropped those variables that have too much missing data, impute data in other variables that might have some missing data, but not enough that you'd want to just drop them. So there are different techniques to do this, but for numerical variables, this will mainly be imputing to the mean where appropriate. For variables, for example, such as annual income, where you're not going to impute, zero annual income for most people, because most people who are applying for loans here actually have earned some sort of money and have jobs. So in this case, the most appropriate course of action would be to impute towards the mean. For other variables, you would want to impute towards zero, For example, for employment length, where the absence of the feature, should be interpreted as, just meaning that the person doesn't have any work experience. And for other qualitative variables and categorical variables, you would want to use the highest frequency class to impute those variables. And the last part is sort of just normalizing features. This is really important when doing deep learning and neural nets. You always want to make sure that your features are normalized in the 0 to 1 domain. Otherwise, your neural net won't be able to converge and work properly. And then also just ensuring that your dependent variable is in the 0-1 set, and that everything is mapped correctly, that there's no sort of text data that might throw off your machine learning models during the training phase. Next, the feature engineering, feature selection phase is another important part of the process where you're looking to extract additional information and try to find and create new variables that might yield more interesting information and capture some relationships between your independent variables. And then as well as create new variables. For example, in this case, when we're trying to actually show internal rates of returns for investors, creating new variables that might capture that. So in this case, as we were trying to create those tools that would show to investors which loans were the highest IRR loans, we had to extract datetime values, which from the date variables that were initially in string format, and then using that to create functions that would allow us to calculate and produce a cash flow schedule for each of our loans. That was a necessary step in the process in order to calculate the net present value of each of our loans based on that cash flow schedule, and then creating an IRR value for that loan, which we would then be able to use when trying to capture misclassification costs and tune some of our model cutoff thresholds in our machine learning phase, which I'll talk about a little more later on. So going into sort of some of the meat of the project itself, which is really the machine learning and deep learning modeling. There were 9 models that I was interested in looking at here. You'll see them in the left hand side table. But really, these are linear models such as logistic regression or linear discriminant analysis, which will really try to find and model more linear relationships in your data. This might be suitable for certain types of problems where those linear relationships already exist. In other types of problems where usually you'll be dealing with large amounts of features, for example, in this case where we have 151 features, you want to be able to have a little more agile models that can model out those nonlinear relationships. And this is where tree assembling methods like random forest classifiers or gradient boosting classifiers come in handy and allow you to create models that are a little more flexible in understanding some of the nonlinear relationships in the data. And then finally, going into, I also wanted to test out some of the deep learning techniques that we learn about in the bootcamp. So I wanted to build a neural net here in this case with 5 dropout layers and 8 neural net layers that would be able to capture, again, similar to the tree assembling methods, some of the nonlinear relationships in the data. And to measure and compare all these models, the sort of the metric that I wanted to use was ROC AUC score, which allows really to capture the impact of both false negatives. False negatives meaning predicting a specific loan as a bad loan when in fact it was a good loan. And the impact of false positives, which would be the converse of that. And the reason for that is it's important when you're an investor and you want to maximize your profit or your internal rate of return to capture both of those things, because a false negative will mean lost interest income, while a false positive is going to mean an even worse alternative, which is loan principal loss, which is where you just lose all your whole entire investment because the person defaulted on you. So that ROCAUC score captures both of those things. There are different metrics that are available, of course, when you're measuring model performance, which I won't go into, but might prioritize or place more weight on measuring the impact of false negatives or false positives. But ROCAUC score in this case was what we decided to go with. So as you see here, the tree ensembling methods were largely outperformers versus some of our linear methods, which was a little unsurprising given the large amount of features that we were dealing with and the complexity of the problem of actually trying to predict how people behave, and repay or don't repay their loans. So in this case, our CABOOST classifier, which is a tree ensembling method, sort of a more recent one, largely outperformed pretty much everything else, and our neural net was second there, with for CABOOST classifier and neural nets, our ROCAUC scores respectively in the 0.84 and 0.81 range. The key takeaways really of this are that the tree ensembling methods are going to largely most of the time outperform linear models when you're dealing with sort of these complex relationships in your data. And in this case, actually, one of the sort of notable exceptions to sort of this general rule was our random forest classifier model was actually a notable low performer, and that would definitely be one thing going back and trying to improve on this project would be to try to see if there would be better ways to tune and adjust the model, the random forest classifier model, to capture some of those relationships better. So next, going with these machine learning results, I was really interested in looking at our CABOOST classifier model and using that as the basis for all of our loan predictions. So in the bottom, on the left-hand side, you'll see here the confusion matrix for our model results. The way to interpret this confusion matrix, this just shows how your model predicted well or badly for different prediction values. So in this case, for example, your CABOOST classifier model predicted 460,000 loans as good loans in the yellow box when those were in fact good loans. So if you go bottom to, if you look at the bottom and the left-hand side values, you'll see where those things cross and correspond, and you'll be able to tell how your model is predicting well in certain cases, or predicting badly in others for predicting good loans or bad loans. And going in on the right-hand side, this was sort of me wanting to visualize a little better and better understand really what our CABOOST classifier model was or how it was classifying and predicting some of these loan values. So to 3D model this, I picked the two topmost most important features by feature importance. Feature importances are essentially available to in any model to see what your most important features are, and you can use that to kind of build additional intuition about what might be interesting for additional feature engineering. But in this case, to output this 3D model or visualization, I picked the two most important features for our CABOOST classifier model, which were annual income, which again is a little not surprising, and then this other variable down here, which captures the amount of credit lines that the applicant has opened in the past 12 months, which typically is a measure or an indicator of how financially stressed the applicant is, and looking for credit. So in this case, you can see that this 3D visualization is showing that for applicants with relatively high annual incomes above the $350,000 range, and who have low amounts of credit lines open in the last 12 months, the model here is predicting that those are generally good loans, as this is the sort of red gradient is showing confidence level above confidence level for it being a good loan. So next, taking again the CAP-based classifier model, I was interested in looking at how to better tune some of the cutoff thresholds for our model. So the way to think about cutoff thresholds is, so in any sort of machine learning model, your model is going to always output prediction probabilities for how confident it feels for one certain prediction or another. So, for example, if I were to feed any loan applicant, data to our CAP-based classifier model, would, for example, tell me that it felt 80% confident that this loan was a good loan. Once you have that prediction probability, the model turns it into a prediction by seeing whether or not it's above or below a certain cutoff threshold that you give it. So really tuning that cutoff thresholds, especially in problems where you have like these, where you have large class imbalances, is very important. And in this case, the way that I thought about best tuning this would be to look at the total misclassification dollar loss for each cutoff threshold, and seeing how that trended across different thresholds. So this just means, for example, varying that cutoff threshold. If I had a 0 cutoff threshold, that means that I'm predicting every single loan as a good loan, which of course, not every single loan is a good loan. So I will have large amounts of principal loss when the good loans that I predicted are actually bad loans. And so that will be captured in this variable, this dollar loss variable. And then I'll be able to see how that trends basically across different values, and see which one is best. Of course, the converse of that is predicting every single loan as a bad loan, and that leads to lost interest income, which is also bad for an investor, of course. Means you'll have 0 returns. So that sort of is the exercise that it's being done here and displayed in this graph right here. So doing this exercise, we found that the optimal cutoff value for our model was 0.73. This makes sense. It makes intuitive sense because you would want your model to be highly confident in predicting a good loan as good on average, versus predicting a bad loan as bad on average. And the reason for that is that it's a lot more costly to predict a bad loan as good due to that principal loss than predicting a good loan as bad, which is just going to result in lost interest income, which is a lot less money than losing your whole investment. So that is what this cutoff threshold graph is showing, and so that's what we went with going forward with our CAP-based classifier model. So going to some of our final results and sort of portfolio construction and optimization, I was really interested in seeing how we could leverage these predictions on the 2018 loan set to then try to allocate capital and see what sort of IRR values we could yield based on this constructed portfolio. So you'll see here this CAP-based portfolio here for 36-month loans. There are 2 types of loans in the LendingClub data. There are 36-month loans and there are 60-month loans. So the loan applicant will actually be paying 36 payments in the case of 36-month loans, and 60-month loans will be 60 payments. So for a CAP-based classifier model, doing that IRR exercise gave us IRR of 7.4% for 36-month loans, and 60-month loans were at about 11%. And you'll see, if you compare that to LendingClub's self-reported historical IRRs for each of those loan tenors, those CAPU's portfolio results significantly outperformed those historical IRRs, showing that there is some alpha to be had from these machine learning models. And then I also was curious to just compare that as well to a baseline model, which a baseline model in this case would just be predicting every single loan is good, which because of the class imbalance, is still going to yield some IRR. In this case, you can see here about 6% IRR for 36-month loans and 10% IRR for 60-month loans. But of course, anybody, with no understanding of extending credit would be able to do this. But this wouldn't be a very effective way of actually targeting good returns. So seeing and comparing our machine learning results against this baseline model kind of gives you a good idea of how to think about your results in the aggregate. So in this case, you can see that our CAPU's portfolio produced 1.5% of model outperformance, of IR outperformance on the 36-month loan, and 1% of model outperformance on the 60-month loans. And the next question out of this is to say, well, how actually statistically significant are these results? And in this case, that question can be answered just by a 2-sample t-test to see essentially how you're how you're taking into account the mean and the variances of your model predictions, seeing how statistically significant those are versus your baseline model. And in this case, you can see that those are significant to the 1% level. So next, the final part of the project was trying to build real-time loan default prediction tools that investors and users would be able to use. So what the left-hand side sort of explains how this is done and what the logic and process of this is, whereas a user on our website will select a loan applicant ID and a model to view. That information will be captured on the web page and will be passed on to a Flask server through a JSON query that the Flask server will then unpack and then pass the observation data to the model that we've trained. So for example, our CAPU's classifier model, and then the model will then serve model predictions to our Flask server, which will then be passed back in another JSON object to the web page, which will be displayed to the user. So I encourage everyone after this talk to go back to the website and play around with those toggles. But essentially, the webpage that we built allows a user to select a loan applicant ID and then see in real time what the model that is also selected is predicting, and how confident the model is in that prediction. And then at the same time, every time that the user selects a loan applicant ID, the Dash app that is hosting all this backend is also outputting information on each applicant and showing, for example, down here in the bottom left, annual income of the loan applicant or FICO score, to kind of allow the investor to build some intuition and contextualize the predictions and see how different models are dealing with our data. So that is the talk for today. I'm happy to stop here and take any questions, or and yeah.
Okay, thank you, Felipe. You actually there are many questions. I try to cover the bulk of them, but anything finance specific related to the industry, I was unfortunately not able to cover. As I mentioned, my background is more in education and criminology and marketing data. So let's see here. I think one of the questions was regarding if you could just talk a little bit about the background of the data set, and specifically how did you address, for example, some of the issues such as the fact that there may be some inherent bias within the data set, such as the data is primarily approved loans. yeah, I don't know if you could speak to that.
Yeah. So, I mean, the data set that we have access to only has, we only have the data for approved loans. We unfortunately don't have the rejected loan data set. So, of course, that is why we see, that partly explains why we have the class imbalance problem that I discussed, where you have more good loans than bad loans, because the ones that are rejected are typically going to be, in most cases, bad loans, and wouldn't be interesting for investors to invest in. So, of course, that's always an issue in the data, those biases, and trying to be mindful of that when training your models, and adjusting for the class imbalance through doing different techniques for cross validation, stratifying the sort of zeros and ones in your dependent variables is always important in order to address that bias, and make sure that your models aren't going into the sort of fallacy of trying to predict more of the majority class, which is could be a really big issue in classification problems like these, where it's important to find and predict accurately the minority class, which are loan defaults, which are going to lose investors a lot more money.
Okay, cool. So there's also another, I feel, I guess, fairly common question from likely the folks that are a little bit more from the finance crowd. They asked if what you may have considered taking into account, for example, the fact that, of course, when it comes to finance data, there is some form of seasonality due to economic trends. And how specifically did you maybe either address that in the LendingClub data set when evaluating this data set?
Yeah, so actually the big advantage of this data set is that it does span it does span a good amount of sort of macro seasonality, where you have 2007 data. Of course, you really only have a year and a half of sort of data that happens during one of the greatest bull markets in recent history, where you're because of that not going to have as many loan defaults as you would in another period where you're going to have an economic downturn. But one of the advantages of sort of the largeness and completeness of the LendingClub data set is that it does span a good amount of sort of macro fluctuations, where you have sort of the 2009 to 2013 period that is definitely encompasses much more severe economic downturn versus other years. So I think that would really be a bigger problem if you only had data, for example, for years 2008 to 2010 or years 2016 to 2018. But in this case, because we have so much data across so many years, that's definitely a little less of an issue.
Okay, yeah, and then I guess two final questions, mainly because of the fact that, and this one I apologize for asking because I was there when grading your project, but it has been a month ago, and tonight I have been kind of, I was not prepared for the rate of questions, so I wasn't able to pay attention again during the presentation. So if you answered this, I apologize in advance. When you mentioned you also built a neural network, was it just was this one of the more standard feed-forward neural networks, or did you use a different neural network structure?
Yeah, that's correct. Yeah, it was sort of one of the more basic structures with 5 different dropout layers, and sort of your standard backpropagation. So yeah, it definitely is sort of not a incredibly complex neural network, but still in this case, as you saw from the results, still rather impressive in some of its classification accuracy versus some of the other tree ensembling methods, which might be expected to perform a little better on tabular data, especially, whereas neural nets will typically be expected to perform a little better on sort of image data, or audio data, non-tabular data. But in this case, it did still perform rather well, and wasn't an incredibly complex neural net. It was more sort of a recursive structure that is sort of your classic neural net.
Okay, gotcha. And also, did you have an ensemble model towards the end, or did you just have a selection of models? Because I do know in your app, you actually have one where it does allows the user to kind of play around with a bit of a portfolio optimization tool kind of in a way.
Yeah, so that is another tool that we built as part of the web framework that I was a little apprehensive to show just because of some of the errors that we saw. But you can play around down here with sort of filtering for different features, and if an investor, for example, was interested in only gaining investment exposure to people that have mortgages, they'd be able to type in this bar right here, mortgage, and it would sort of filter all values that, in this case, the app isn't responding correctly, but it would.
I think I warned you even during the project presentation the first time that don't link don't link the app. And I think this time with around 100 attendees, it would. It looked like it did load.
No, I think it just it just loaded the rest.
Okay, no worries.
So in this case, this would be another way if an investor just wanted to filter for specific characteristics, for example, state or loan purpose. If they only wanted to gain exposure to people that were looking to consolidate their debt, as opposed to some of the more interesting loan purposes. There are some in here that are wanting to fund some of their wedding expenses or other things, then they'd be able to do that. Yeah.
Awesome. Okay. Sorry. So I think one of the questions, kind of the final question I'll just ask about would, well, first, can you Slack me also, Felipe, just the GitHub link that you showed, and I will plug it into the chat.
Definitely. Yeah.
And also this way, folks can look at the code accordingly. For whatever reason, your last comment in the chat box did not pop up.
Got it.
So
okay.
If you could just Slack it to me instead, I'll copy and paste it into the chat. Folks, there's also a fair amount of questions that I think are going to be out of scope of today to answer. Like, for example, such as why a random forest score is so low. There's a lot. That's a rabbit hole in and by itself on why certain models may perform better than the other. So yes, Felipe, if you could just Slack me, and then in the meantime, also you could stop sharing. I will also share my screen just to give out also some promo codes for the attendees as well.
Awesome. Thanks everyone for listening.